Now we start the chapter that most students hate, proving mathematically. We're starting in chapter 2.1, which is inductive reasoning and conjecture. But again, we must start with the new vocabulary. Inductive reasoning. Okay, don't forget, inductive reasoning is reasoning that uses a number of specific examples to arrive at a conclusion. Okay, usually in a pattern. You can usually observe something in a pattern, and then for you to make an educated guess of what the next one is called inductive reasoning. Okay, conjecture. A conjecture is an educated guess. You know, what is going to be the next number in the pattern? Well, you can work that one through the fact of the previous examples. For instance, Fibonacci's sequence goes 1, 1, 2, 3, 5, 8. From inductive reasoning and a conjecture, you can make out that the next one's going to be 13, purely and simply because if you add the previous two numbers together, you get the following example. A counterexample, that's the easy one. A counterexample is very simply when you can come up with any argument that proves the previous argument false. So for instance, if I turn around and say all prime numbers are odd, all you have to do is come up with the number 2. Number 2 is the only even prime number, but at least you've given a counterexample and proved it's correct. So now let's have a look at patterns and conjectures. Obviously the first one, in example 1, movie times 8:30, 9:45, 11 o'clock, 12:15. Well, going from each of these to this one, and from this one and to this one, you are adding 1 hour and 45 minutes. All you then, sorry, not 45, 15 minutes. So all you then have to do is just work the pattern out, make sure you've got the correct amount, and that's 1 hour and 15 minutes. So the next one would be 1 hour and 15 minutes after that, which will give you to 1:30 p.m. Okay, patterns, you know me with patterns, they're the difficult ones for me, but when you look at the diagram here, the one good thing about this one is they give you the numbers underneath, and again it's looking what happens to get from this number to this number. Okay, here you add 6, here you're adding 8, the next one you're adding 10. So you can see what they're doing is actually adding onto that. That one's adding 12. So the next one, which is your conjecture, would be you're going to add 14. And 14 onto 40 will give you 54. You can see here is a typical example question. Make a conjecture about the value of each geometric relation. List or draw some examples that support your conjecture. Here is the sum of two odd numbers. Well, then all you have to do is set out it. But typically students always make wild and wonderful numbers up. Just start with the lowest. So 1 plus 3 will give you 4. Okay, 1 plus 5 will give you 6, etc., etc. See how you go. Okay, and here's the perfect solution that you've come up, making a conjecture. Now, don't forget you do this in science anyway, but to make a conjecture, the sum of two odd numbers is always an even number. Simple, easy, but look at the numbers they've used, small numbers. So don't start coming up with making huge numbers right at the beginning, keep them relatively small. There's a few more for you to have a practice on. You've already done, well, now you've done the sum of two even numbers, okay? The relationship between A and B, if AB equals CD and CD equals EF, work it through. A lot of geometry in that one. Okay, the big one, all right, and here is where we get information. This is a bit like the weather forecasters, if when they're trying to predict things. Here is one with a hairdressing salon. When you get a question like this, do what they've said. Always make a graph that best supports your data before you start trying to answer questions. Once you've made the graph, then it's here's the graph of this information. Look how easy it is now to look at a graph and see visually what the next or what the pattern is actually happening to it. Okay, so make a graph, simple, easy. Counterexamples. This is easy for you, okay? It's easier to prove something that is false than it is true. Think about a solving systems where you've got to multiply both of your original equations. Well, if everything's true, you've got to go all the way to the answer for X or Y or whatever letters they use and plug it into one or both of your original equations to make sure that it's true. If you find a counterexample, even for instance, if the first line they had to multiply it by 2 and one of them they didn't quite do that, then straight away, as soon as you've got to that next line, you've proved it false. And the moment you've proved it false, you've found a counterexample. Simple, easy. Again, here's finding a counterexample using algebra. If n is a real number, then n squared must be greater than n. All you've got to do is prove it false. Well, when n is 1, the conjecture is false. Since 1 squared is not greater than 1, it equals it. As soon as you've done that, boom, you've got an answer. You've proved it as a counterexample. So always try and find the simplest one, rather than going up in numbers and squaring huge numbers, etc., etc. Start simple, start at 1. If necessary, start at 0 and then go to 1. But most of the time, starting at 1 is a normal, easy place to start. Okay. The next one, it's here for you, but this is where